Modern PV manufacturing processes produce cells with a relatively large variance in their power output capability. Panel manufacturers seek to reduce their variance by assembling panels from pre-sorted cells. Nevertheless, panel models on the market today still have a plus or minus 3% variance in power output. Moreover, each panel has a slightly different MPP current. When several panels are connected in series, traditional centralized inverters cannot draw the optimal current from each panel. Instead, the inverter selects the current that gives the average peak power point of the string or array. This peak power is always less than the theoretical sum of the individual peak power points of every panel. The power loss resulting from this panel mismatch amounts to 3% to 5% on average. The power loss from partial shading occurs when part of a panel is shaded, causing different levels of illumination on the cells in the panel. When a panel is partially shaded, its voltage may reverse. This can result in panel damage due to overheating. All PV systems prevent this in one of two ways. The panel bypass diodes conduct, causing shaded panels to lose from 1/3 to all their power. Alternatively, the inverter readjusts to the current flowing in the whole string to a lower value acceptable by shaded panels. In either case, power loss in particularly shaded arrays is significantly greater than the reduction in the illuminated area, because power output is also lost by non-shaded cells and panels. In typical residential roofs, shading cannot be completely avoided. On average, partial shading losses amount between 5 and 25%. Inverters will only function between a predefined minimum and maximum voltage. If the solar array produces too little voltage, for example, due to high temperature and short strings, the inverter will reduce the string current below the optimal operating point until this situation is resolved, resulting in power loss. Undervoltage is unavoidable in many cases where short strings are required. A survey estimated that over a quarter of PV installations in California experienced power losses of at least 15% due to undervoltage. The efficiency of the inverter maximum power point tracking depends upon its algorithm's ability to identify the array's peak power point at any given time. Changing environmental conditions can have a significant impact on how effectively traditional inverters can identify this peak. For example, shading can cause the array's power curve to exhibit more than one maximum power point, and many MPP tracking algorithms are not designed to handle these local peaks efficiently. When the MPPT is mistakenly locked on a local peak, the MPPT efficiency falls dramatically, creating static power losses. Dynamic losses are directly related to the speed and the accuracy of the MPP tracking algorithm. The peak power point can move quickly due to frequent changes in irradiance levels on windy, cloudy days. Traditional inverters will struggle to keep tracking MPP with these changing conditions. Power losses due to suboptimal MPP tracking typically vary between 3 and 10%. To summarize, traditional PV systems suffer from various inherent power losses stemming from a centralized topology. Blueline Solar MI increases energy output by up to 25% while reducing system cost and simplifying design and installation. The Blueline MI solar system is comprised of 3 key elements. The Blueline Power Box, which is integrated on each solar module in place of the junction box, a simplified, highly reliable inverter, and an integrated panel-level monitoring system. The Blueline Power Box optimizes power harvesting by performing MPP tracking of each panel individually, while keeping the string voltage fixed. Here we see the IV curves of 2 solar panels fitted with Blueline solar power boxes. You can see that the MPP point is different for each panel. As you will recall, traditional systems cannot handle this mismatch and will adjust to an average point, resulting in power losses. In contrast, The Blueline MI solar system easily manages MPP tracking individually for each panel, harvesting the optimum available power. The same capability also ensures that the Blueline MI solar system will harvest more power in partially shaded situations. The shaded panel produces as much as it can, while other panels in the string are not affected and continue to produce at their maximum peak point. In traditional systems, high temperature or shorter strings may lead to power losses due to string undervoltage. Blueline MI solar systems prevent this loss by maintaining string voltage fixed at optimal DC to AC conversion point, while independently controlling the panel voltage. Last, panel level MPP tracking can better identify the global peak of the power curve. It also allows for noticeable faster tracking compared to centralized inverters, especially during dynamic weather conditions. To summarize, our Blueline MI solar system can increase energy production by up to 25%.